Astronomers believe that the universe started with a Big Bang around 13.8 billion years ago. The first objects to form were stars, and then later galaxies. Early stars were thought to have only consisted of hydrogen and helium, with no metal being present. And this means that as the universe evolved, more metal would be found in stars that formed later and later. And the same would happen to galaxies. In this model, early galaxies would contain mainly stars of earlier generations with very little metal content. Now astronomers have observed some of the oldest galaxies and were shocked to discover that they contain a rich mixture of elements, including an abundance of metals. In an electric and plasma universe, this story comes as no surprise. So let's examine the facts of this story. Now let's examine the first problem in this story, and that is of the distance or the age of these galaxies. The only way to determine the distance to these objects is through redshift. The oldest objects should have the largest redshift as they would be moving away from us at the fastest rate, and the space in between us will have expanded the most. This would stretch the light into the red end of the spectrum. Except we know that this is not always the case. There are other processes that can cause the light to be shifted to the red end of the spectrum. Firstly, plasma in the space between us and the object can cause the light to be shifted more. I have produced a separate video outlining some of these mechanisms. Now some of these mechanisms, like the tired light concept as modified by Tom van Vlaanderen, would still imply that these objects are further away, and others might imply that it is simply more material in between us and the object causing an increase in the shift to red. It may also be possible that there are intrinsic processes going on within the galaxy which causes the light it emits to be shifted to the red end. Arp looked at quasars and determined that part of the redshift that we saw was due to some mechanism going on within the quasar shifting this light. One more recent way to interpret this is to consider Lerner's quasar model. Here there would be a huge cloud of spiraling plasma surrounding the central plasmoid, as well as dust and other gases which are pulled along with the inflow. So it is possible that the same mechanisms that we discussed above, so this plasma that surrounds it, could cause the shift to the red end of the spectrum. Particularly considering that around one of these plasmoids, the plasma itself would be highly energized. The same mechanism might also occur within the heart of a galaxy, affecting the overall appearance of the light received. The second point is that there is no need for a Big Bang. More than likely, our universe is infinite and has existed for an eternity. This therefore means that galaxies simply come into existence and die out all of the time, anywhere in our vast cosmos. Now, this does raise one interesting question, and that is, why do we see the differences in the chemicals in different galaxies? Assuming that these chemicals are generated in the same way, shouldn't the majority of galaxies have a very similar fingerprint? If transmutation is going on, like in SAFIRE, then we would see these chemicals being created everywhere. Well, one of the pieces we need to consider is that SAFIRE didn't always produce transmutation. There were certain conditions that were required for this to occur. So it is possible that the reason we see differences is because the conditions are not the same everywhere, meaning some areas might be more efficient at doing this than others. It is also possible that the galaxies might draw in material from the remnants of older gas clouds left behind from previous galaxies, or siphoned off from elsewhere, and these might contain a different ratio of elements than the other galaxies. Now, another big problem with this study is that in order to see these ancient galaxies, they needed to develop a novel technique to observe them. By using quasars which sit behind the galaxies, they were able to observe what light was absorbed by the distant galaxy to work out what elements were present. Now, I don't need to repeat the whole story about the problem with quasars. See my other video if you're interested in that. But there are two very important things to consider from Arp's work. Firstly, quasars are not the distant objects we assume them to be. The redshift is due to other reasons we have already discussed. Secondly, and most importantly, Arp realized that there was a correlation between the quasars and a host galaxy. In fact, he speculated that quasars were ejected from the host galaxy. So are the quasars that we are using to observe these galaxies simply the quasars that came from this galaxy? Now, this doesn't necessarily bear any direct relevance to the study in terms of the absorption, but it does again hint at this concept that Arp was talking about, the fact that there is always this correlation between a quasar and a host galaxy. As always, be brave, be curious, the truth is waiting for us. Until next time.